So next lecture is about 3D heterogeneity. So the problem is that the images we are collecting, they typically belong to different conformations of the macromolecule that we are interested in. And these multiple conformations may come from discrete states, so that, for instance, the macromolecule is bound or not bound to a particular ligand or to a particular factor, or also it may be because of some continuous heterogeneity, so that some part of the macromolecule is moving. And maximum likelihood has been a very successful tool to tackle this problem, and it has its own problems like attraction and so on, but in general it works, and just to make sure that you are getting the right extraction, the right classification, you should run the process several times so that you are sure that the labels that are attached to each one of the images are the correct ones, because otherwise the classification is a relatively unstable process. So the thing is that let's say that you have 100,000 images, and then this 100,000 images you classify into 4 classes. 3 of them may be the same one, simply because you have asked for 4 classes, but you didn't have 4, but in practice you had only 2. So the biggest class is split it into 3 classes. So here you have the 2 classes that are distinct, and what we have in maximum likelihood is we have somehow a data fidelity term. So we are looking for the classes, so for the volumes that maximize the fidelity to the data, and this has been very successful. And here you have another implementation of the same maximum likelihood idea, and here is well, the different classes that they found. So they found 3 classes rather than just 2 in this data set. And then for instance, if we are extending XMIP to have CL3D if you want. So CL2D was very successful, and we have borrowed some of the ideas like hierarchical clustering, which could be also borrowed by some other algorithms, or even the existing ones, or the ones maximum likelihood. So you may first put all the images together into a single structure, and then divide in 2, and then these 2 divide in 4, and even you allow the images to change from one class to the other. But what we have found is that the first split is crucial, and this first split is randomly done in most algorithms. And what we have seen is that if the first split, there are many times in which the first split doesn't allow a correct classification, and that might be behind this problem of instability of the classification. And we have also seen that the classification is better performed if it is done according to several criteria, similarity criteria, not just one. And this maximum likelihood just looks at one of them. Which all these ideas make sense. I'm not criticizing anyone. It is just to give an idea of what are the different possibilities that you have when you are classifying data. And Bayesian a posteriori adds an extra term to the goal function. This extra term is the prior. So you have 2 terms now to maximize. One is the data fidelity, the other one is the prior on the kind of classes you are reconstructing. And this is a very useful statistical technique if you have the right prior, and it also helps a lot when you have a lack of data. So when you don't have much data, then the prior helps a lot to identify what are the underlying parameters. And this prior uh, makes the assumption that the one that is this Bayesian approach that we have in the field, it makes the assumption that the Fourier components are independent and Gaussianly distributed with zero mean and unknown variance, whatever. So this unknown variance goes in the denominator of the update of the volume, and this means that if you lower the variance of the if you lower the variance of or these estimates are multiplied by a constant t, and if you lower this constant, then at the end the effect is a low pass filter of the volume. So that means that one of the things that this Bayesian prior is helping is trying to keep the resolution low by or not to boost the frequencies at which we don't have enough evidence that the signal is above the level of noise. So this is just a measure of the signal to noise ratio and a low pass filter according to the low pass to the signal to noise ratio, but it has been very useful. Maybe one of the objections we could do is that these assumptions that the Fourier coefficients are independent, Gaussianly distributed with zero mean and unknown variance, they are not fulfilled for actual structures. Like if you analyze 500 PDBs and you convert them into atoms, into densities using these electron scattering factors, then you realize that Fourier coefficients are not independent from each other, they're not Gaussian, they don't have zero mean. So these assumptions are not fulfilled, but still they have been useful because they impose this as a low pass filter. And something else that has helped a lot, especially to escape from local minima, is the stochastic gradient descent. And this stochastic gradient is simply the observation that to make or to calculate classes, you don't need to use all images in the data set. So if you have 1 million images, you don't need the 1 million at the same time, but you can take a random, a small subset of them, and then update your classes, and then take another random subset and update your classes again. And because the random subsets are random, the goal function that maximizes the likelihood or the maximum a posteriori or whatever goal function that you put on them will be different from one iteration to the next. They will all share a commonality if they're coming from the same structure or same kind of heterogeneity, but so they will all share some commonalities, but they will not be exactly the same, and this not being the same helps to remove the possibilities of getting trapped into local minima. So they're not absolutely foolproof, but they work typically very well. And something else that it was pointed out a few years ago by Joachim Frank is what is the stability of the different classes. So if you go from iteration t to iteration t plus 1, how do the images stay in the same class, or they are jumping from one class to the other? And this is relevant because if, for instance, you see that most of the images at T are staying either in class 1, they stay either in class 1 or they move to class 2, and the same happens with class 2, either they stay or they move to class 1, so probably classes 1 and 2, they cannot be very well separated. then class 3 is very well separated, and classes 4, 5, and 6 cannot be separated either. So this is a very interesting analysis that can be done to check what is the real number of classes that you have in a data set. Then recently, well, not so recently, but a few years ago, 5 years ago, it came out this idea of focus classification. I find it very useful. That is, sometimes the classification, or you are interested in a region and you want to make classes of that region alone. And for that, what you can do is to remove computationally the projection from the rest of the macromolecule. So for instance, let's say that we have a macromolecule that has two distinct parts, and we are interested in analyzing the heterogeneity of this red part here. So what we could do is segment the yellow part, then compute the projection, and the experimental image is actually the projection of the yellow plus the red part plus the noise and the CTF, and then we can subtract the yellow projection as to get the red part. So ideally, this is a very good approach. In practice, sometimes this subtraction is not as successful as in this slide, and then there are some parts of the yellow that remain in the micrograph, and yeah, it is more difficult to make the classification. But ideally, it is a very good approach to analyze a particular area. There was also this idea of doing bootstrapping. This was Pavel Pensek 14 years ago, and the point is, okay, so let's say that I have some heterogeneous region, but I don't know which one it is. So what I could do is to make bootstrap reconstructions of my data set. So I take my projections, I assign angles, and then I bootstrap. I make bootstrap sets, so that is, if I have 100,000 images, I construct volumes with 100,000 images, but with repetition, so that some images may appear more than one time. And then by analyzing the covariance of these or the variance of this set of reconstructed volumes, I will be able to identify areas that are varying and identify these regions where I should concentrate. And this idea is not used so much, probably because this idea of bootstrapping, if you have 100,000 images, all the bootstrap samples will more or less have the same reconstruction. It will be difficult to identify the covariance region. But for low number of particles, I think this is very, very nice tool. And we can extend the idea of variance to covariance. So in variance, we can identify that there is a region or a couple of regions that vary more. But with the covariance, what we can realize is that these two regions synergistically change. So when one is bright, the other one is dark, or the opposite, or both are bright or dark at the same time. So these synergies or concerted actions of the different regions, they can be captured by the covariance. And the covariance, for instance, here we have another illustration of that. So let's say that we identify that these two regions are varying in our map, but the covariance map could tell us that when this red area is present, the blue one is not, or when the blue one is, then the red one is not. And this cannot be done by the variance alone. The variance would be saying these two areas are changing, but it doesn't tell you what are the concerted movements or the concerted presence or absences that are in a map. And there have been many people approaching this problem of the covariance, and so far the state, I would say, it is that the covariance can be computed at a very low frequency, at very low frequency, so we cannot analyze the fine details and the fine movements with the covariance tools that we have at hand. And then we have this other branch of continuous heterogeneity rather than discrete heterogeneity. So macromolecules are flexible objects, and they may move in different directions with different concerted movements again. So for instance, here we might have this head of the polymerase that is moving from left to right, but at the same time the head is moving from the back part to the front. And these we have a video here where we can see both movements at the same time. So the point is, you may use, in that work it was normal modes, to identify possible directions of movement, and then you analyze you compare the experimental images to these normal modes and identify which are the actual movements that were taking place in your data. That was a drawback in that work, that was that you had to choose which normal modes you wanted to explore, which gives which can bring a bias in analysis, and we have extended it now to the use it is here, to the use of spherical harmonics to be able to get rid of this user-based decision. But the point is to do the same kind of analysis. Okay, so another approach to this continuous movement problem has been done with this multi-body refinement that somehow borrows the ideas from the focus classification. So you analyze each of the regions independently, and then somehow you find the relative movement between the different regions. And this is implemented in Reliant as the multi-body refinement. And then you can compare, so these two approaches compare a volume that is deforming to the images. This one is comparing volumes. So let's say that you use a discrete classifier and identify discrete classes in your data set. And now you wonder, what is the sequence, or what is the relative, what are the relationships between all these classes that I have found? So for instance, here is some simulated example in which this part of the molecule was moving down, and it was considered with some other movement on the other side that was also moving down, and then these two were also in motion concertedly. And so we have two axes of movement, and that means that the relationship should be kind of cross, and this is actually what we recovered with this tool. And I have shown in this slide the examples with a phantom, because it is very nicely understood, but in the paper we applied it to real data, and we were also able to find the relative orientations or the relative sequence of all these maps. And there have been some other approaches on continuous heterogeneity based on manifolds, and the point is to map the input images into some into some low dimensional map that allows you to identify kind of trajectories or different clusters of these images at the input. And there another different approach is this one. In this one, they were making random subsets of the input data and then computing different volumes, and then from these different volumes they were computing a PCA of the volumes, so that they could analyze the presence of different regions in the landscape of volumes, and somehow they could be translated into energy landscapes. But this idea of translation into energy landscapes is the same for all these techniques analyzing continuous heterogeneity. So what is new here is the use of the PCA. So this is just the mention that we are extending the work on normal modes to get rid of the choice of the right normal modes, and for that we have changed completely the base, so they are no longer normal modes. But the first results, we already see that, for instance, with this data set of Joachim Frank on a ribosome that has 10,000 images, it has been used as a benchmark for 3D classification, and originally it was classified in 2 classes. And when you see when you look at the continuous heterogeneity of that data set, and you make a plot in 2D, you project all that information into a 2D plane so that you are able to see. What is identified is that one of the classes was kind of the central core of this continuous heterogeneity, while the other class was just a mixture of the remaining. And in the remaining we had also a couple of subclasses that were not originally identified. And if you have continuous movements between 2 structures, so let's say that you have the ribosome in 2 different conformations, then you can analyze also what are the local forces and what is the nature of those local forces that transform one volume into the other. So if we deform continuously one volume into the other, these forces would have something, some rotational components and some stretching components, or stretching or compressing. So here we have then the decomposition of those forces into rotations. So you see that this part doesn't move, this part is moving more or less collectively, this part is moving a lot, and this is the strain analysis, and the strain analysis shows that most of the macromolecule is not moving, but this part is stretching or compressing much more than the rest. So in conclusion, heterogeneity, I would say, is currently one of the most limiting factors, especially because of this instability and the difficulty of getting a stable class for each one of the images. Priors are useful if they are true, so the ones that we are using are not so true, but they are useful in the sense that they help to keep the noise low. We have already talked about the problem of the class stability, and the number of classes is also a problem, because you don't know a priori what is the number of classes, so you would like to have some help in choosing this number, or not the number of underlying classes, because probably this is an infinite number because of this continuous movement, but the number of classes that can be identified. And we have already seen this focus classification. That is a very good way of making the analysis of only one part of the macromolecule. We have been talking about the variance and covariance matrices that are nice ideas for helping you to concentrate on different areas. And we have also been talking about the continuous heterogeneity. So this would be all for this talk, and see you in the next one.